Alright, so welcome back to another video. So in today's video we got this this double integral that's definitely going to give you nightmares, I can tell you that for sure. The double integral of from 1 to infinity and 0 to 1 of -1 to the power fractional y. I almost said factorial when I made that previous integral back a long time ago. I accidentally said factorial. It's supposed to be fractional. Y fractional multiplied by the fractional of 1 divided by 4 times floor of y root of x minus 1 divided by the 4 times floor of y root of the fractional of x plus sine of y squared plus 1 dx dy. So you can clearly see that there's a lot of things going on. We have well, for one, we got a double integral. We also have that there's a -1 as the base. So integrating that is going to be really tricky if we're dealing with like doing some elementary integration, which that's not going to be possible in this sense. I already mentioned the fractional part. That's going to be a bit of a doozy. And let's actually get started. Let me actually write the definition of what defines fractional parts. So fractional parts is supposed to be defined as the equation, let's say we have u fractional, so that's just simply just equal to u minus the floor of u. So basically we're taking the fractional part of the integer of, well, not of some integer, of whatever your integer added with the fractional, and then we're just subtracting it for that. Okay, so that's taken into account. So let's actually just ignore this -1 to the power fractional y. Simply because this is being integrated by dy. So how about we just focus on integrating this in respect to dx. So basically we're focusing on the integral from 0 to 1 of so we're integrating this from 0 to 1 of the fractional of 1 divided by the floor of y of x, and then subtract that from, so I'm going to write the denominator first. So this is basically just 1 floor of y and the root of the fractional x plus sine of y squared. Okay, and then the numerator is 1, and then plus 1. All that in respect to dx. Okay, and using we can actually split this into 3 different integrals. So this is all basically just my summations of integrals over here. Simply, yeah, right here is good. So simply this is just 3 integrals, 0 to 1 of the fractional of 1 divided by 4 times the floor of y root of x dx. Then subtract the integral 0, 1 of 1 divided by 4 floor y, and the root is fractional x plus sine of y squared dx from 0 to 1 of 1 dx. Okay, obviously you could tell that integrating this definite integral, that's pretty elementary to do since this is just a constant being integrated. So we'll just save that to the side for later. So let's now actually focus on integrating each of these. So let's actually focus on our first one over here. So okay, so first integral is the fractional. Okay, so how about we're going to do a u substitution. So we do a u substitution. How about we let u equals the inside of our fractional. So let u equals 1 divided by 4 times y, or floor of y root of x. Okay. In other words, we can actually just write this as the exponent is a fraction. So in other words, this is just the same thing as x to the power -1 divided by 4 times the floor of y. Okay, and because we're going to be doing some substitution later, so now the next step we want to do is how about we actually let x be by its, get x as a standalone variable. So when we do this, we have, so this would mean I would just take the -4 times floor y root. So I get this, and that's just equal to x. Okay, and therefore just differentiating both sides, then I have that it is -4 times floor of y divided by u to the power 4 floor of y, and then plus 1 du, and that's equal to dx. Okay, so now that we have our pieces, now before we actually do any like substitution, everything in terms of u, we also need to change our bounds as well. Okay, so we have our new bounds. So that means when we have that x is equal to 0, okay, so then that would have to mean that this is actually going to approach infinity. Okay, and then when I let x equals 1, then that's just still going to be 1. And for the sake of it, because well, I'll do that. I'll do that later. Next step, I was thinking about skipping steps, but because this is we have a lower bound that's actually a bigger number than the upper bound, then we have to actually switch our bounds of integration. That'll turn into a negative, but I'll just do this one by one at a time. So everything inside the fractional, that'll be replaced with u. So this is u. And then multiply our substitution dx. So this is -4 floor y divided by u to the power 4 times floor of y plus 1, and then du. And now I'm gonna like I said, switch our order of integration so that we have that it's from 1 to infinity, and that's a negative. That negative will cancel out. And because this is in terms of u, it does not depend on y, so pretty much I can just factor that 4 times floor of y outside of the integral. Okay, so that means we have 4 times the floor of y, and then multiply with our integral from 1 to infinity of the fractional of u, and then divided by u to the power 4 floor y plus 1 du. So, okay, now next thing we want to do is, now because we have that, the fractional, we have inside the integral a fractional of u, so we have the definition of the equation that the fractional u is equal to u minus the floor of u. So then how about I just replace this with our equation. So this is 4 times floor of u, or y, multiply by 1 to infinity, and then replace this with u minus the floor of u divided by u to the power 4 times floor of y plus 1 du. Now notice that there's a u over here, and we have that it's the power of u. Basically, I can actually split this into partial fractions. We're not really decomposing, but I can split this into 2 fractions of the same denominator. Therefore, that means, well, okay, let me get to that in just a sec, but let's focus on the floor of u. So floor of u is the greatest integer function. So anything you have like the floor of pi is just equal to 3, or the floor of e is equal to 2. So we're actually when we're doing our bounds of integration, we're gonna have to do this one by one at a time at each x value. So what we can do is by taking the definition of our fractional, we can actually write this piece in terms of sums. So specifically, I can rewrite this as 4 times the floor of y, and then multiply by, well, okay, so this is actually our summation series. So start that sum is from k is less than or equal to 1, so it's an infinite series. And then we have our integral, so we're starting at 1, so that means we can start at k, and then all the way up to k plus 1. Okay, and then we have that u is divided by u to the power 4 floor y plus 1, but just factors out, so it's multiplied by y, then it's canceled, so I have that it's just 1 divided by u to the power 4 floor y, and then subtract from our, so we're doing this from each k's, starting with our index k's 1, so we can just place that as k, and then divided by u, okay, u to the power 4 floor y, and then plus 1 du. Now all that's left is, now we can actually calculate this definite integral. So how about I write this back in red, and this is just simply just calculating the this definite integral over here. Okay, so let's just focus on this integral. So this is from k to k plus 1, and I can actually rewrite this so that the inside expression is in fraction form, so we just have just the base and then its exponent. So rewriting this, we can actually write this as u to the power negative 4 floor y, and then subtract with k, and then multiply by u to the power negative 4 floor y, and then minus 1 du. Now integrating this, so we're gonna get that it's over here, right? So this is 4 floor y, and then the inside expression of this integrated integral. So we have that it's u, and then minus 4 floor y plus 1, and then divided by negative 4 floor y plus 1. Then subtract k times u to the power negative 4 floor y, all this being divided by negative 4 floor y. Next is to evaluate this, but let me actually like fix this expression so it looks nice, and that way calculating this will be a little bit easier. So this is 4 floor y. Then inside expression is now rearranging our terms, since everything here is commutative. So this is simply, we could just write this as k to the k times u to the negative 4 floor y divided by 4 times floor of y, and then subtract that from u to the power negative 4 floor y plus 1, and then divided by 4 floor y minus 1. Okay, and then this is being evaluated from k plus 1 to k. All right, that kind of looks a little crooked, but it's not really an issue. Okay, so now let's actually calculate our bounds. So we have, this is 4 floor y, then this is from this means we get k, then k plus 1 to the power negative 4 floor y, then divide that by 4 floor y. Subtract that from k plus 1 to the power negative 4 floor y plus 1, and then we divide that from 4 floor y minus 1. Okay, so that's 1. Okay, and then next is minus k times k to the negative 4 floor y, divide that by 4 floor y, and then subtract that from k to the power negative 4 floor y plus 1, and then all this being divided, and then that being divided by 4 floor y minus 1. So now let's actually continue to simplify this expression out. So right here, So next, now also I'm gonna rearrange some terms and also distribute the 4th floor y into this entire expression here. So doing all of that, we will get the following. So let me write this in parentheses. So we get that it's k divided by k plus 1 to the power 4th floor y, and then subtract that from k to the power, or k divided by this is to the power k to the k to the 4th floor y. Okay, so that's 1. Then well, not subtract, add, and then this one's going to be a big one. So this is 4th floor y multiplied by k plus 1 to the power negative 4th floor y plus 1, and that's being divided by 4th floor y minus 1, and then multiply plus 4th floor y multiplied by k to the negative 4th floor y plus 1, and then being divided by 4th floor y minus 1. If you pay attention to this expression, we can actually factor this out. So specifically, we can actually factor out 4th floor y divided by 4th floor y minus 1. So therefore, this means that the following expression can be rewritten. So I'm actually just going to put back the summation. So our sums that we were dealing with earlier. So this is the sum, and then we're starting from k is greater than or equal to 1, so it's like infinite. So we have that the following. So we have it's 4 multiplied by, or the floor of y divided by 4 times the floor of y minus 1, and then this is 1 divided by k to the 4th floor y minus 1. Next is 1 divided by k plus 1, and then to the power 4th floor y minus 1. Okay, so then, like I said, let's just factor out the 4th floor minus 1, and then subtract from this expression here. Also, if you pay attention here, this can actually k divided by k to the power 4th floor, 4 times floor of y. It actually can be rewritten as 1 divided by k to the 4th floor y minus 1. So that's just another way to rewrite this expression. So in case you're wondering, so let me see, 1 and then k 4 floor y minus 1. So if you're wondering where this term came from, it's just basically we simplified this expression out, so to get this. Okay, and now all that's left is just minus k. And also there's the negative out here. That's simply because I just rearranged the terms here and then I just factor out the negative. So this will just end up be positive on the parentheses, and then this will end up as a negative. If you're curious, that is. K plus 1, and then 4 floor y. Okay, and now you might be thinking to yourself, what's the next step? Well, obviously we want to simplify this whole expression out, but it doesn't look like it'll get easier from here. However, there is one thing that what we can do, and it'll make things very nice and interesting. If you pay attention closely to specifically this expression and this expression, you'll also notice that this is actually the same formulation. This is actually the same thing as writing the riemann-zeta function of 4th floor y minus 1. Okay, and then if you pay attention to this expression over here, then you'll get that this is also the same. 3 written as 4th floor y minus 1 and then minus 1. Okay, now if you pay attention closely, we're dealing with subtraction. So this is actually, the Riemann-zeta functions are actually going to cancel out, but you're also just left with -1, but the negative distributes there, so we get a positive. Okay, so now, therefore, we can write our, our simplified expression. Well, not yet, just for now, for the time being. So this could be rewritten as 4 times the floor of y, then minus, or divided by 4 floor y minus 1, and then minus our series, because we still have to deal with this here. So this is minus k divided by, or k is greater than or equal to 1, and then this is the same thing as written as 1 divided by k to the power 4th floor minus 1 minus 1 divided by k plus 1 to the power 4 floor minus 1, and then plus 1 divided by k plus 1 to the power 4 floor y. Okay, and now I know what you're thinking, like how do we get these two terms here? So what I did was, and I guess I can show the work here. So put this off to the side, maybe over here is good. So what I did was, I can actually add and subtract. So we're focusing on this expression specifically. That's how we get this decomposition. What we can do is I can actually add and subtract a k plus 1. So let me see, just rewrite this again, k plus 1 4 floor. And so what I did was I actually just add and subtract, the 1. So, and I can also group this. So this is k plus 1 minus 1, and then divided by k plus 1 to the power 4 floor y. Okay. And so the way I group this is that therefore they share the same base. So therefore I can rewrite this as k plus 1 to the power 1 subtract 4 floor y. Okay. And then also I can actually rearrange the terms here. So negative 4 floor y, and then plus 1, I can factor out the negative. So it's negative 4 floor y minus 1. So therefore that's actually how it ends up in the denominator for this piece right here. And then we're left with minus 1 divided by k plus 1 4 floor y. Okay. And just simply just rewrite the same thing. It's we get this the same expression as 1 divided by k plus 1 4 floor y minus 1, and then minus 1 divided by k plus 1 and 4 floor y. And that's exactly how we got this expression here. And this is subtraction, don't forget. So this is minus, and then distribute the negative here. That's the end of a positive. Okay, so just a little heads up in case you guys were just curious. So I'm just gonna erase this, and you make room for the rest of the work as well. So, okay. So now coming back into here. So now what you'll notice is, just like before, we have that this is also equivalent to the Riemann-zeta function. I got room, yeah. This is the Riemann-zeta function of 4 floor y minus 1. Okay. And this is also the same expression that just as previous before. So this is the same thing as Riemann-zeta of 4 floor y minus 1 minus 1. Okay, and now same thing, just like before, we're gonna get some terms that cancel out. So these two will cancel, and then we're just left with -1 but the negative will distribute, so that'll be a positive 1. So that can be moved outside, and now rewriting this, we're gonna get that it's 4 floor y divided by 4 floor y minus 1. And then this piece, they cancel, and we're just left with negative 1. So it should be negative, you get a positive. So then we'll end up with, well, and then the negative comes back, so that means this is b minus 1. And then subtract that with our summation. So the infinite series, so this is from k is greater than or equal to 1 of this piece of 1 divided by k plus 1. And then to the power 4 floor y. Okay, so now we want to pay attention that 1 divided by k plus 1 to the power 4 floor y. That definition is also written as a Riemann-zeta function as well. Specifically, this piece is the same as the Riemann-zeta function of 4 floor y, and then subtract 1. So it's basically just it just move its index in a sense. So that's why there's the negative 1 piece comes from. We're subtracting a piece that it didn't start from that index at 1, even though they're written differently anyway. So okay. That means rewriting this, or not rewriting, but like simplify everything out. We have that it's 4 floor y divided by 4 floor y minus 1, and then minus the Riemann-zeta of 4 floor y, then subtract 1, or well, plus 1 now, because now the ones will cancel. And so we're just left with that. It's just 4 floor y divided by 4 floor y minus 1, subtract the Riemann-zeta of 4 floor y. Okay, so that's our first integral right here. So it's equal to this. So how about I underline this in black so we already know like what our pieces are. So over here, this is our first integral. So now we have to calculate our second integral, specifically this one, the integral from 0 to 1 of 1 divided by the 4 times floor of y root of the fractional of x plus sine of x, sine of y squared. Okay, so let's focus on this. Okay, so we have this, but what I can do is I can actually replace the sine of y squared with just some random constant. Why is that? It's because the integral we're evaluating in is respect to x. So simply, y does not vary in the world of x. So we can actually just replace this as, I'll just call the sine of y squared just some constant a. So, okay, so now, this expression right here, this integral, is actually the same thing as rewriting it as 4. So this is 4 floor y and then the square root of x dx. Okay, so you might be asking yourself, why is that the case? So particularly, let's think as this holds as the fractional of 1 plus a. It's actually going to equal to the fractional of a. So now looking closely, so we think about for all x's that's in the open interval from 0 to 1. So the fractional x plus a, it would have to increase from the fractional of a to 1. And then it would have to actually return back to 0, and then it'll continue to keep increasing from 0 to the fractional of a. So this pretty much means that it's going to cover all its positive values greater than or less than equal to, or yeah, greater and less than the fractional of a in that open interval 0, 1. So therefore we can actually justify by saying that we replace our fractional x plus a is simply just equal to x. And also keep in mind that we also have a constant for floor y as our index root, so it's also treated as a constant as well. Okay, so now we have this. Now we can actually write this as a base. So it's no longer in fraction form. So this is 0 to 1 of x to the power of -1 divided by 4 floor y dx. Okay, so now we just use power rule. So this is just x to the so this is just x to the -1 divided by 4 floor y plus 1, and then this being divided by -1 divided by 4 floor y plus 1. Integrate this from 0 to 1. Okay, but this is easy to see that if you plug 0, so you're just going to get the whole term as 0. And we'll also get that if you plug 1, then it's pretty much for any exponent, it's always going to equal 1. So this is basically just 1 divided by -4, or -1 divided by 4 floor y plus 1. And okay, so how about I write here? Let me show this little work on how I can simplify this out. So this is just -1 4 floor y plus 1. Simply, that's the same as just -1 plus 4 floor y, and then all this being divided by 4 floor y. Now, same thing over here is just 1 divided by this whole thing. But under division, I can actually just flip the reciprocal, and so therefore the evaluated integral of here is supposed to be 4 floor y divided by 4 floor y minus 1. Okay, nice. So now we have our pieces. So okay, we just underline this. That's our second integral. So therefore, now I already said that there's a 1 here. That's obviously you can easily show by just calculating the definite integral that you're just gonna get that that's just equal to 1. So rewriting this integral, we're gonna get that. Okay, just rewrite everything. So this is the fractional of 1 divided by 4 floor y root x. Then subtract that from 4 floor y. I'm just writing the denominator for now. And fractional of x plus sine of y squared. Okay. 1, then plus 1 dx. Okay, now we substitute our pieces. This is simply just, so this is 4 floor y divided by 4 floor y minus 1, and then subtract that from our Riemann-zeta function of 4 floor y. Okay. And then this is subtract from minus 4 floor y divided by 4 floor y minus 1, and then plus 1. So therefore, simply the 4 floor y divided by 4 floor y minus 1, they're just going to cancel out. And I'll just rewrite our rearrange our terms, so we're just left with a negative Riemann-zeta of 4 floor y and then plus 1, so therefore we get that it's 4 plus 4, or oops, this is Riemann-zeta. So it's Riemann-zeta of 4 floor y. Okay, cool. Alright, so that's just our iterated integral over here. So now we actually have to iterate this again in terms of in respect to y. Okay. So now all that's left we have to do is integrate this in respect to y. So now integral from 0 to 1, or 1 to infinity, excuse me. So this is from 1 to infinity of -1 to the power fractional of y then multiplied by 1 plus the Riemann-zeta of 4 floor y. And then dy. Don't forget about that. dy. Alright, cool. So now, obviously the next choice, the obvious thing you could do is you can actually just distribute the -1 to factorial, fractional, I did it again, factorial, fractional y, and distribute it into our 1 plus the Riemann-zeta of 4 floor y from there. But it's not actually as simple as you think it's going to be. Really, it's not going to be easily integrable in that sense. So, what can we do to fix this? Well, okay, so I'm actually going to write this in red as well. So what we can do is we can actually replace the 1 plus Riemann-zeta of 4 floor y. Instead, we can actually replace that with the fractional of the Riemann-zeta of 4 floor y. And I'll show you the work on why that's equivalent with this. Okay, so I'm just gonna write what we can replace. And we can replace this with Riemann-zeta 4 floor y. Now, simply using the definition of our fractional, it's basically just u minus floor of u. So in this sense, where it's Riemann-zeta of 4 floor u, and then minus the floor of the Riemann-zeta of 4 floor u, or 4 floor y. Everything I said for u is supposed to be y. Oops. Now, now let's actually write this in definition of the using series. So this is actually the same with Riemann-zeta. It's the infinite series from infinity, n is equal to 1 of 1 divided by n to the power of 4 floor y. Okay, and then we can subtract that with the floor of the series, infinite series of when n is equal to 1 of same thing and 4 floor y. Pay attention that now let me rewrite this series again one more time. N is equal to 1 and then 1 divided by n 4 floor y, and then minus. So let's actually expand this series out just a bit. That means we're doing so expand this out. This is we get 1 to the power of 4 floor y, then plus 1 divided by 2 4 floor y, and then so on and so forth. So 1 3 4 floor y, and then plus dot 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 floor of that. So if you look closely, if we were to take this as a partial sum, so we take limits. So if we take the limit as n approaches infinity of this series from n is equal to 1, and I'll just say capital N since there's already a lowercase n, and capital N approaches infinity. So we're gonna get that obviously that this is going to well, since this is all with fractions we're dealing with, clearly you can see that this is actually going to be bigger than 1. But what I can do is that, so if I take the floor of that, then we're actually going to get the floor of this expansion is 1, simply because we have that 1 divided by 1 raised to the power, that's 1, then plus everything here, which is our expanded as fractions, but that's going to increase bigger than 1 as it's when you take that, the limit is approaching infinity, but you take the floor of that, it's actually going to be just equal to 1. So therefore, just rewrite this again, then this is again simply just the Riemann-zeta of 4 floor y, and then minus 1. And we have shown that this is equivalent to the fractional of Riemann-zeta of 4 floor y. Okay, so with that, I'm going to with that, I'm going to replace our 1 plus Riemann-zeta 4 floor y with the fractional of Riemann-zeta 4 floor y. But simply there's a negative, so to fix this, I can factor out a negative. This is actually supposed to be a minus, that's my bad. that's a minus over here. And now it makes sense, like with the distribution of the negatives. This is minus, and this is minus. Okay, cool. So now let's actually replace this. So we're gonna end up with negative. So this is from 1 to infinity of negative multiplied by -1 to the okay, so we have a fractional y over here. So how about instead I actually replace that with the definition of our fractional function. So basically I'll just write y minus floor of y, okay? And then we replace this with our fractional of riemann-zeta for floor y. Now obviously there is a floor y in this expression over here. So this means that I can write this using the series expansion, just like we did the same definition earlier, like over here in particular. So this means I'll just write this as so we're replacing everything with everything for floor for y in terms of k, like partitioning, because we are going to deal with from 1 to infinity. So we're gonna have to do this, like take steps each time. So that's why we're dealing with the sums. So therefore, I'm just going to replace everything with floor y with just k's. And if I were to put k here, so it doesn't depend on y anymore, so that means I could just factor out, put that outside of the integral. But I'm going to put that behind the summation. And the same thing for the negative here. So therefore, this is rewritten like the following. Infinity k is equal to 1 of fractional of riemann-zeta of 4k, and then we have our integral starting from k to k plus 1 of -1 y minus k dy. Now let's actually focus on integrating, just focusing on our integral over here. Oops, drop my marker. Okay, so let's focus on this. So this means I have so let's see, integral k plus 1 of -1 y minus k dy. But going back to complex analysis, I can actually replace the -1 and rewrite that as its polar form, and write that as let's see, k plus 1 of e to the I times pi to the power I times pi of y minus k and dy. Okay, so that means by integrating this, I get that this is just exponential, so this is e to the power I y minus k. Okay, so just doing, use substitution, so this would be divided by I times pi of between k to k plus 1, and we get that this is just so we just simply put in our k plus 1 for y, and so on, and k as well. So the following expression is written as e to the power I pi divided by I pi, and then subtract that, that this is just 1 divided by I pi. And okay, but e to the I pi, just replace that, we just get that it's -1, and then and I'm gonna get that it's just simply just -1 minus 1, so this is just equal to -2 divided by I pi. Hold on, let me rewrite that. This is just -2 and then I pi. I'll just put that back into our series. Negatives cancel, so this means we're back with, gotta go back to the ground. So that means we're back over here. So this means negatives cancel, so I'll get that it's 2 pi I, and then multiplied by our Riemann-zeta, or our series of the Riemann-zeta, or the fractional of the Riemann-zeta. Okay, so now the next part is I want to rewrite the fractional part of the Riemann-zeta 4k into another series. So we're actually going to end up with a double series. So actually, this is actually the riemann-zeta of, or the fractional of the riemann-zeta of 4K is simply actually the same definition as this, but if we were to rewrite this as a series, simply it's the same as, so that means I'll just write, this is infinity to k equals 1, but we also have our second series infinity n equals 1 of, or actually, so not that our starting index is 1, it's actually equal to 2. So our starting index is n is equal to 2 of 1 divided by n to the power of 4k. So that's the definition of what we're using for Riemann-zeta. Simply from over here earlier, it's just another rewritten expression of the fractional of Riemann of 4k. Okay, so now next step what we can do is I can actually rearrange our series. So that means when we evaluate the series for 1 over n of 4k, we're going to start with our index with k in particular. So, okay, so rewriting this to pi I, some series from n is equal to 2, and k is equal to 1 of 1 over n to the 4k. Now, actually, you can see that this is convergent using the comparison test, and what we can, and then using the partial sums formula, we can actually rewrite 1 over n4k as the following. It's convergent to, see, it's 2 pi I, and then back to our sum, n is equal to 2. This is the same thing as n to the 4 minus 1. Okay. So now we just have to calculate this. What we can do is I can actually split this into partial fractions, or use the partial fractions decomposition, obviously, but I'm not gonna show all the work for that. I'll just, you can actually check this to yourself. If we can decompose the fractions, we actually get that the following here is 2 pi I, then multiplied by with our sum, n is equal to 2. Simply, we're going to get that it's 1/2. I'll just write this a decimal, so this is 0.5 n squared minus 1. And then subtract that with 0.5 divided by n squared plus 1. Okay, so focusing on the term 0.5 divided by n squared minus 1, you can clearly see that this is actually convergent by using the comparison test. And specifically, the finite answer that this converges to is simply just, so rewrite this back, this is 2.5, and then it's actually convergent to 3 over 8. And now we just have to deal with this last piece over here. Okay, so that we have 2 over pi I, then 3 over 8, and then minus 2 over pi I. Then we have this series expressed, this series 0.5 n squared. Let me actually rewrite this a bit. This is 6 divided by 8 pi I. That's simply just 3 divided by 4 pi I, and then minus 1 pi I, and then with the series 0. Fix this. We have the infinite series, infinity, and then n is equal to 2 of 1 divided by n squared plus 4. Okay. So now all we have to do is just evaluate this last series over here. So now you might be thinking to yourself, how do we expand this? So this is going to I'm going to deal with some complex analysis here. So let me rewrite this in red. So this n is equal to 2, 1 over n squared plus 1. Equivalently, that's actually can be rewritten as the following. It can be written as -1 plus, and you can check this yourself, 1/2 multiplied by infinity, and then n is equal to -infinity of 1 divided by n squared plus 1. Specifically, this series here is actually, this is known as the Laurent series. That means we're just basically dealing with series of terms that deals with the negative indexes. So that's also rewriting as that. Then we can actually use the residue. We can actually use the residue theorem to actually calculate this series over here. So rewrite as So this is -1 plus 1/2, and of the residue of, let's see, let me just write this, z squared plus 1, and then then multiply by e to the 2 pi I z minus 1, and then numerator is 1, and then we're evaluating from our poles. So z, some pole over here for that, that's like an integer. Okay, so now to calculate this residue over here, so obviously we need to find our poles. But actually what we can do is we can actually apply Jordan's lemma and solve this residue specifically in this form. So this is z squared plus 1, and then e 2 pi I z minus 1 z star, the integers. So that means we have our, again I said use Jordan's lemma to write that as following, so we get that as -2 pi I, and then multiply by the residues of, so our poles again is actually z squared plus 1. You decompose that, you're going to get that the poles are actually z is equal to positive and negative I. So now we just have to calculate our poles. So this means calculate our z. Our pole is when z is equal to I. So z approaches I. This is basically z plus I, and then e to the 2 pi z minus 1 divided by 1. Okay. And simply put, that's just equal to 1 divided by 2i, and then multiply by e to the -2 pi minus 1. Okay. And the next pole we need to calculate is the z is approaches -I. So this is just 1 z minus I, and then e 2 pi z minus 1, but that's also simply just -1. It's just a negative, so it's 2i, and then e to the positive 2 pi minus 1. Okay, so we have our two poles over here. We just underline this. Now that we have our both our poles evaluated, so let's actually calculate the following over here. So this will be this will be -2 pi I, then multiply by our 1 divided by 2i, then e to the -2 pi minus 1, and then plus, well, now subtract, because there's the negative over here. So subtract from 2i, then e to the positive 2i minus 1. We calculate this, you simplify this out, we get that it's just -pi divided by e to the 2 pi I, or just 2 pi. Well, actually, this is supposed to be negative. That's a negative over here. This is supposed to be e to the -2 pi minus 1, and then plus pi divided by e to the positive 2 pi minus 1. Okay, cool. Now, when we simplify this out, again, a second time, we're going to get that it's simply just going to equal pi multiplied by 1 plus e to the -2 pi, and then divided by 1 minus e to the -2 pi. Okay, cool. So we have this. So now let's actually substitute that back. So I'll actually just write on the side that this is actually just our evaluated Laurent series. So this is just So now, if we substitute everything back in, we get that it's -1 plus 1/2 of pi divided by, or I'll write this up, 1 plus e to the -2 pi, and then divided by 1 minus e to the -2 pi. Okay, and that's just going to equal to -1 plus pi multiplied by 1 plus e to the -2 pi, and then divided by 2 times 1 minus e to the -2 pi. Alright, cool. So that's our that's basically our expanded series over here. So that's just alright. Now everything's coming together as one, so we just plug everything back in. So we have 3, 4 pi I minus 1 over pi times I. Substitute that back in with -1 plus pi, and then 1 plus e -2 pi divided by 2 1 minus e to the -2 pi. Okay. And now let's just simplify everything out. Let me try to get a common denominator. So this is just 3 over 4 pi I. Then that'll be a positive. So get a common denominator for I, and then 4, and distribute over here. And then this is subtract. So this is let's see, pi. Let's see, the pi's will cancel out, and then we're left with 1 over 2i. So that means what I can do is I can hold on, let me write this out as full first. 1 plus e to the -2 pi, and divided by, and let's see, so we have pi's will cancel, so we're just left with 2i, and then then I'll just multiply the i's from both the top and from the numerator and the denominator, so that they cancel, so that we end up with so this will be a positive term now if I were to multiply the i's from top and bottom. So therefore this term comes first. So therefore we get that the following answer is equal to I, then 1 plus e to the -2 pi divided by 2 multiplied by 1 minus e to the -2 pi, and then subtract this. This is, let's see, 3 plus 4, 7 divided by 4 pi I. If I multiply I top and bottom, it's a subtraction, so we get that it's 7i divided by 4 pi. Alright, there we have it. That's our conclusion. That is our final answer over here. Ooh, that is a lot longer than I thought it would be. So I mean, this is pretty much worse than the other integral that I did